Alright everybody, in this video we're going to finish up our conversation about limits. We're going to talk about limits at infinity, we're going to talk about infinite limits, and talk about one-sided limits. Then we're going to bring up the topic of continuity, what that means at a point, what that means over an interval. And in order to start, I want to briefly review the epsilon-delta definition of a limit and kind of go over that more visually. That's why I've drawn this diagram here. And I also want to introduce a little bit of mathematical symbols. So our definition of the limit tells us that the limit of f of x as x approaches some value c is equal to L if and only if, that's what the IFF means if you have seen that before. The limit as x approaches c of f of x is equal to L if and only if for any value of epsilon greater than 0, there exists some value of delta greater than 0, such that, or actually this is backwards, such that the absolute value of f of x minus L is less than epsilon, and the absolute value of x minus c is less than delta. So you might see it written this way. This symbol means for any, this symbol means there exists, and this one, not to be confused with this one, this means that x is an element of some set, but when you see it written this way, this signifies such that. So what this says is the limit as x approaches c of f of x is equal to L if and only if for any epsilon greater than 0 there exists a delta greater than 0 such that the absolute value of f of x minus L is less than epsilon and the absolute value of x minus c is less than delta. And just a brief review of what these inequalities tell us. If we solve here, we would say that this is true if x minus c was less than delta, meaning if x was less than c plus delta. It would also be true if the negative here, negative x minus c, was less than delta. The reason being the absolute value bars would undo that negative. Solving here, we get that x minus c is greater than negative delta. You have to flip the sign when dividing by negative, and x is greater than c minus delta. Taking these two things together, this tells us that x is on the interval between c minus delta and c plus delta, which is pictured here. Here our x would be 2, and here you would have 2 plus delta and 2 minus delta, and it would be any of the x values in between these two bounds. Similarly here, this is telling us that f of x exists anywhere within epsilon of L. So that tells us within L plus epsilon and within L minus epsilon. Once again pictured here, this would be our L, our limit here. We would say that the limit as x approaches 2 of 2x would equal 4. And so this is our proposed limit. This bound right here is 4 plus epsilon, and this bound right here is 4 minus epsilon. And you can see that that would intersect with our delta values. And so what this definition tells us is that for any value of epsilon, there will always be some corresponding values of delta that will yield an interval of input values, of x values, that once put into f of x will result in output values, f of x values, that are going to be within epsilon of our proposed limit. And what this definition tells us that if for any value of epsilon greater than 0, no matter how small we make this, that there will always be some associated x values that will, when plugged into f of x, result in f of x values that are within epsilon of our proposed limit. If that's true for any value of epsilon, then we say that the limit exists at that point. So that's just a brief overview of exactly what that means with a little bit of a visual explanation here. Alright, now that we've reviewed a little bit, let's get into some new material. So here we have a graph of f of x, just some arbitrary function. And as you can see, as we get closer and closer and closer to this point 3 here, from the negative direction, the function tends to follow some predictable pattern. But then after this point 3, it changes behavior drastically and starts to exhibit the behavior of some sort of different function. And so what we're interested in here is what the limit of this function is as x approaches 3. And you might ask yourself, well, if we're approaching this from the positive direction, and we can notate that as such, the limit as x approaches 3 from the positive direction, indicated by this little positive superscript here, of f of x, well, it appears to get closer and closer and closer to 2. But as we approach from the negative direction, which predictably you could say was given by a little negative superscript, what does that tend towards? Well, it seems to get closer and closer and closer to the value 4 here. And interestingly, these two values do not agree. And so this can't possibly, neither one of these proposed limits could satisfy our formal definition here, because our formal definition is encompassing values that are within delta of our point of interest, but on both the right and left sides. That's what this absolute value inequality tells us. And as you approach from the right, it approaches this value, 2, but as you approach from the left, it approaches 4. And so neither one of these could be our limit. And so for that reason, well, the limit at this, as you approach this point, doesn't really exist. As you approach from one side, it tends towards something which is wildly different than what you get as you approach from the other side. But what if we weren't dealing with x values within delta to the right and left of x? What if we were just dealing with x values within delta to the left or right? This should be a negative. Let's fix that. 3 minus delta and 3 plus delta. And so basically what we're getting at is here is, do these limits exist? Does the limit as x approaches 3 from the positive direction exist in the limit as x approaches 3 from the negative direction? And if we wanted to write that, we would say if and only if for any epsilon greater than 0, there exists some delta greater than 0 such that the absolute value of f of x minus L is less than epsilon, that the resultant values of y are within epsilon of our proposed limit, and the value of x falls on the interval greater than c but less than c plus delta. What is that? That's just this interval here. And so if this is true, then one might imagine that the limit as x approaches c from the positive direction of f of x is equal to L. And that is our formal definition of the one-sided limit from the positive direction. And very, very similarly, we're going to write our definition as we approach some point from the negative direction. One-sided limits from the negative direction say if and only if for any epsilon greater than 0, there exists some delta greater than 0, such that the absolute value of f of x minus L is less than epsilon. And here you would say that x is greater than c minus delta, but less than c. And once again, that would be dealing with these x values here. Then we say that the limit as x approaches c from the negative direction, f of x, is going to equal L. And that should make sense. Now, what happens if the limit as we approach from the positive direction and the limit as we approach from the negative direction does agree? What if it tends to approach the same point? One might imagine that the limit would then exist at that point and it would be equal to that function. But let's take a look. Well, the absolute value of f of x minus L would still be less than epsilon. We can notate what I'm talking about here. If the limit as x approaches c from the positive direction is equal to L, and the limit as x approaches c from the negative direction of f of x is equal to L, then, oh my god, that's so bad. Then the absolute value of f of x minus L will be less than epsilon, and well, what would happen to x? Well, this would be true for values of x that are greater than c minus delta, that's coming from here, but it would also be true for values of x that are less than c plus delta from the other definition of the approaching from the positive direction. And if this is true, then that's just the formal definition of the limit. That just tells us that the limit as x approaches c of f of x is equal to L. If there is agreement between x values approaching from the positive direction and x values approaching from the negative direction, if that yields the same value, then the limit does exist at that point, and it is that value. All right, and I promise that we're going to look at some specific examples of one-sided limits. However, very rarely do you see one-sided limits that exist in nature that are not piecewise functions like this. This would be considered a piecewise function wherein it changes behavior to a completely different function at some point. Very rarely do you see one-sided limits that approach definite values like this unless they're at infinity or negative infinity, or unless they're approaching infinity or negative infinity. So before we look into some specific examples of one-sided limits, because I don't want to do something like this, I feel like that's creating an example to fit the problem rather than analyzing natural functions that you would find in nature, which is something I prefer to do. So before we look at a specific example of one-sided functions, we're going to have to talk about infinite limits and limits at infinity. All right, so let's talk about infinite limits first. So I want you to imagine a function f of x is equal to 1 over x squared. And so what would a graph of this function look like? Well, we could draw our y and x-axis here, x-axis. And we could imagine that at the points -1 here and the points 1 here, this would approach y value of 1, right? And then it would just sort of follow a curved path down from there on both sides. It would look something like this. And it would get closer and closer and closer to the x-axis. As x got larger, this denominator here would get exponentially larger, and it would get closer and closer and closer to 0. And so we say that this would asymptotically approach 0 as x tended towards infinity and as x tended towards negative infinity. But what happens as this gets closer and closer to 0? Well, if you plug in like 1/2, for example, 1 over 1/2 squared would equal 1 over 1/4, which would equal 4. Well, what if we plugged in 1, like 0.1, for example? Well, 0.1 squared is equal to 1 over 0.01, which is 100. And so it seems like as we get closer and closer to 0, this tends to get bigger and bigger and bigger. It would look something like this. And so you might imagine that the limit as x approaches 0 of this function, 1 over x squared, would equal infinity. But how can we prove that? Like, how could we formally write that out? Well, with infinite limits, what we say is that if, and only if, for any value of m greater than 0, there exists some value of delta greater than 0, such that the value of f of x is greater than m, and the absolute value of x minus c is less than delta. If all of this is true, then the limit as x approaches c of f of x is equal to infinity. And so what does this tell us? Well, this tells us that for any value of m, no matter how big we make it, there is some x value within delta of c that f of x winds up being bigger than that value of m. If no matter how big we make that value, there will always be some x value that's sufficiently close to c such that f of x is greater than that value of m. If that's true for any value of m, well then the limit there has to equal infinity. And so let's try to prove that with this function here, with 1 over x squared. So first I want to just say that f of x is equal to 1 over x squared. So let's just assume that this winds up being greater than m. Well, if we multiply both sides and divide by m, then what we would get is 1 over m is greater than x squared. And then I could take the square root here, and we'd see that x has to be less than 1 over m, 1 over the square root of m, if I took the square root of both sides. So now let's talk about the formal definition. Here we're looking as x approaches the value 0, so the absolute value of x minus c in this case would be x minus 0. This is going to be less than delta. And let's say if delta is less than 1 over the square root of m, if is less than or equal to 1 over the square root of m, then what's going to happen? Well, then the absolute value of x would be less than 1 over the square root of m. And then let's square both sides. And so here we'd get x squared. This is always going to be a positive number no matter what x is, so we can get rid of those absolute value bars, is going to be less than 1 over m. And if we invert this, this is going to tell us that 1 over x squared is greater than m. And so we've just proven that if delta is less than or equal to 1 over the square root of m, then 1 over x squared here, which is our f of x, will be equal to m, no matter what value of m we put here. And so for this reason, therefore, we say that the limit as x approaches 0, f of x is equal to infinity. Now let's talk about a different function. Instead of 1 over x squared, I want to talk about the function f of x is equal to log of x. And if you're not familiar with logarithms, what log of x means is that the value of log of x is going to equal the power that you have to raise 10 to in order to equal x. So in other words, if 10 to the power of x, if 10 to the power of y is equal to x, then log of x is going to equal y. That makes sense. So log of 100 would equal 2. Log of 1000 would equal 3. This is the power that you have to raise 10 to in order to equal 1000. It's 3. The power you have to raise 10 to in order to equal 100 is 2. That's what logarithms are. So what would a graph of log of x look like? Well, if we draw y and x axis here, axes, draw it all out. Let's talk at the point 1. What power would you have to raise 10 to in order to equal 1? Well, anything to the power of 0 is equal to 1. So the function at this point is equal to 0. And then as you go out further into the positive x direction, we just established that log of 10 would equal 1. So there would be some point here, we call it 10, and that would equal 1 on the y-axis. And then the next point that would be defined as a whole number would be 100. Log 100 would equal 2. And the distance between these 2 points would be 90. And then the next point would be 1000, and that would equal 3. And so the distance between 1 and 2 would be 90, and the distance between 2 and 3 would be 900. So this is a graph that continues on forever with a decreasing slope. It would look something like this. And what about as this gets closer and closer and closer to 0? Well, let's think about log of 0.1. What power would you have to raise 10 to equal 1 over 10? Well, that would equal negative 1. And the log of 0.01 would equal negative 2. And the log of 0.001 would equal negative 3. And so as you get closer and closer and closer to 0, this value is going to get bigger and bigger and bigger in the negative direction. Or maybe I should say smaller and smaller and smaller. It just depends on how you look at it. And so this would look something like this. And as you get very close to the point 0 here, it would grow rapidly towards negative infinity. And so you might posit that the limit as x approaches 0 from the positive direction, that's very important, of the log x function, you might hypothesize that this is equal to negative infinity. But how can we prove that? Well, very similarly to an infinite limit, we're going to say that if, and only if, for any value of m greater than 0, there exists some value of delta greater than 0 such that the value of f of x is less than negative m and the absolute value of x minus c is less than delta, then we say that the limit as x approaches c is of f of x is equal to negative infinity. And in this case, since we're just dealing with a one-sided limit here, what we want to show, which I said we'd come back to, here we are, but what we want to show is that f of x will be less than negative m, and that's x will be on the interval greater than c, but less than c plus delta. And in this case, c would be 0, so we're talking about the interval between 0 and delta. So let's do that. If we, f of x here is going to be log of x. And if we assume that this is less than negative m, what does that mean? What does x have to be in order for this to be true? Well, if we raise both sides to the power of 10, 10 to the power of log x is just x, which is less than 10 to the power of negative m. And let's put this as our condition for delta. So if we say that delta, if delta, or whoops, almost wrote it out. If delta is less than or equal to 10 to the power of negative m, then what happens? Well, here, x has to be less than c plus delta. In this case, c is 0, so this is just x saying x being less than delta. And so if we write that here, x would be less than 10 to the power negative m. And if you took the log of both sides, this tells us that the log of x will be less than negative m. And so if delta is less than equal to 10 to the power of negative m, then f of x is going to be less than negative m for any m greater than 0. And x has to be on the interval where it's greater than 0 and less than delta. And because of this, we have sufficiently proven that therefore the limit as x approaches 0 from the positive direction of log x, we've proven that this is equal to negative infinity. All right, let's press forward here and let's keep talking with limits at infinity and at negative infinity. These are actually pretty simple, and this will conclude our conversation about limits. These are probably the easiest of all. And so let's think of a function, for example, f of x is equal to 1 over x plus 2. What would this look like if we were to draw a graph out with our y and x axes? Y, x. If we were to draw this function onto this graph, you can imagine that at the point x equals 1, this would evaluate to 3. So we can write that on here. Let's draw 3 here, equal there. And as this got closer and closer and closer to 0, it would get larger and larger and larger because 1 over 1/2, for example, is 2. And then 2 plus 2 is 4, so this tends to grow as we get closer and closer and closer to 0. But what about as we move in the positive x direction? This is going to get smaller and smaller and smaller. That should be obvious. And it's going to approach 0, probably. And then we have the plus 2 here. So this is going to evaluate to 2 at infinity. We can imagine that that would likely be the behavior of this function. But we are interested in how we would prove that. And so sketching that would look something like this. Would asymptotically approach 2. But how would we prove that? We say that the limit as x approaches infinity of some function is equal to L if and only if for any epsilon greater than 0 there exists an n greater than 0 such that for any x greater than n the absolute value of f of x minus L is less than epsilon. What does this tell us? This tells us that for any epsilon greater than 0, no matter how small it is, if there exists an n greater than 0 such that for any x greater than that value of n, f of x will be within epsilon of L. If that is always true for any value of epsilon, then we say the limit as x approaches infinity of that function is equal to our proposed limit, RL. Right, so let's walk through how we would prove that for this function. As x approaches infinity of this function, we would expect the limit to equal 2. And so to start, what would this inequality look like? Well, our f of x value would be 1 over x plus 2, and our proposed limit here would be 2. We would assume that that's what would happen to this function, and this would be less than epsilon. And you could see that this is going to cancel. You'll just be left with absolute value of 1 over x being less than epsilon. And so what if we were to say that the absolute value of 1 over x is less than epsilon? Let's just assume that that's the case, and let's see what has to happen for that to be true. So looking at this, if we wanted to get this in terms of x, we would just flip both sides. We get that the absolute value of x is greater than, remember when you take the inverse you have to flip the inequality, 1 over epsilon. And now, how does this help us with our definition of the limit? Well, if epsilon is greater than 0 and x is greater than n, and n, if we set that equal to 1 over epsilon here, n is equal to 1 over epsilon, then what happens is, because x is greater than n, we write that x is greater than 1 over epsilon. And what I want to point out here is that since we're dealing with the limit as x approaches infinity, this is only going to be dealing with positive numbers. That is to say that this is equal to the absolute value of x being greater than 1 over epsilon. And now we take the inverse of both sides. This is equal to 1 over the absolute value of x, or the absolute value of 1 over x is the same, being less than epsilon. And this is also equal to the absolute value of 1 over x plus 2 minus 2 being less than epsilon. And this sufficiently proves that the limit as x approaches infinity of f of x here is going to equal 2. And if we wanted to write this more formally, we could say that for any epsilon greater than 0, there exists an n equal to 1 over epsilon, which would imply that n must be greater than 0. If epsilon is greater than 0 and n is 1 over epsilon, then n must also be equal or greater than 0. N must also be greater than 0. Such that for any x greater than n, the absolute value of 1 over x plus 2 minus 2 is less than epsilon. Therefore, the limit as x approaches infinity of 1 over x plus 2 is equal to 2. And I do want to talk a little bit about what this actually means. This is telling us that any x greater than n will yield y values that are within epsilon of our proposed limits. So, for example, if we wanted y values or output values that were within 0.01 of our proposed limit, if we wanted an epsilon equal to 0.01, then what this is telling us is that we would have to plug in x values greater than n, n in this case being x must be greater than n, which is 1 over epsilon, would be 0.01, which is equal to 100. And so we would have to look at x values past the point x equals 100. All of those x values past that point will be within 0.01 of our proposed limit too. If we wanted y values within 0.001 of our proposed limit 2 here, for example, we would have to look at x values greater than 1 over 0.001, which is equal to 1,000. So for any x value past 1,000, it's going to yield y values within 0.001 of 2. That's what this is telling us. And so really this might be more accurate to say there exists n greater than or equal to 1 over epsilon, such that for any x greater than n, this inequality holds true. I encourage you to work through this on your own just to see. Like, for example, if we had n equal to 2 over epsilon, when you were to work through this process on your own, you would find out that absolute value of 1 over x plus 2 minus 2, our absolute value of f of x minus L in this case, would be less than epsilon over 2, which is certainly less than epsilon, of course. And so this is really true for any value of n greater than or equal to 1 over epsilon. For any that's going to make true that for any x greater than n, this inequality will hold true. All right, we're in the home stretch here, and thank God, because I'm running out of space, I'm actually going to make a little bit more here. I'm going to delete some of this stuff. Just stuff like this. Fill in the space. The last thing that we have to talk about is limits at negative infinity. And so for this, let's talk about the exponential function y equals, or I'll say f of x equals. F of x is equal to e to the power of x. What does this function look like if we were to graph it? And I'm going to do this like this since we're talking about limits at negative infinity. I want to make sure to get a substantial portion of that negative x-axis on here. So what's this going to look like? What's e to the power of 0? Anything to the power of 0 is just 1. And then as you move forward, the function is going to increase rapidly. It's an exponential function. And then what's going to happen as you go towards the negative direction? E to the power of negative 1 is equal to 1 over e. E to the power of negative 2 is equal to 1 over e squared. So this is going to get closer and closer and closer to 0 exponentially fast. So it's going to look something like this. And it's going to asymptotically approach 0. This is very ugly, but you can see that this is approximately the behavior of the function e to the x. And so we're going to ask ourselves, well, what's the limit of this function as x approaches negative infinity? What's the limit of e to the x as that happens? And we say that the limit as x approaches negative infinity of some function is equal to some value L if and only if for any value of epsilon greater than 0 there exists n greater than 0 such that for any x less than negative n, the absolute value of f of x minus L is less than epsilon. This is very similar to our when we deal with limits in the positive infinity direction, limits as x approaches infinity. You can see this is very, very similar. We're just saying for any x less than negative n instead of an x greater than n. And so with our function here, our proposed limit as x approaches negative infinity, this is probably going to get closer and closer to 0. And so let's test that. If we put our f of x here, that's just going to be e to the x, and our proposed limit is 0. This is going to be less than epsilon, right? And so this is equal to the absolute value of e to the x being less than epsilon. And for all real numbers, e to the x is going to be greater than 0, right? This is never going to be a negative number. There's no number you can put in as an x value that will cause e to the power of x to be equal to a negative number. So therefore, what we could say is that the absolute value of e to the x is equal to e to the x. There's no difference there. That is to say that this is going to be equal to e to the x being less than epsilon. And once again, I'm running out of space, but here we can just take the natural log of both sides. We get that x is less than the natural log of epsilon. And we have to be careful here. We want our x to be less than negative n, right? And so we want negative n to equal the natural log of epsilon. And so that means that n must equal negative natural log of epsilon, which is the same as natural log of e to the power of negative 1, which is the same as the natural log of 1 over epsilon. And so what happens? If we plug in x being less than negative n, we would have x being less than the natural log of 1 over epsilon. Right? This is equal to x being less than the natural log of epsilon. If we take e to the both sides here, we get that e to the x is less than epsilon, and this is equal to the absolute value of f of x minus L, right? It's the absolute value of e to the x. Maybe we should be more specific. This is equal to the absolute value of e to the x minus 0 being less than epsilon. So this is sufficient to prove that the limit of e to the x as x approaches negative infinity is going to equal 0. And if we wanted to write this more formally, we would say for any epsilon greater than 0, there exists n equal to natural log of 1 over epsilon such that for any x less than negative n, the absolute value of, again we want to be specific, e to the x minus 0 is less than epsilon. Therefore, the limit as x approaches negative infinity of e to the x is equal to 0. And I do think it's worth adding here that the same thing is true as well. We're looking at any values of x that are less than negative n. So if this is true for n equal to this value, then it's also going to be true for any value of n greater than this, right? Because then negative n would be a even larger negative number, a smaller number, and x being less than that, of course, is going to be closer and closer and closer to the limit, right? And I was initially tripped up here. This is a little look behind the curtains because let's try, for example, and I'm kind of running out of space, so I'm gonna have to make some more. I have to delete some of this and fill that in. Let's try this. Let's try in, just as an example, being equal to the natural log, or 2 times the natural log of 1 over epsilon. Well, this is equal to this quantity squared, right? So this is equal to the natural log of 1 over epsilon squared. And so what happens now when we put that x is less than negative of 1 natural log of 1 over epsilon squared? Well, when you put that negative there, this is the same thing as saying that x is less than the natural log of epsilon squared, right? Raise e to the power of both sides, I guess the way that you would say that. This is saying that e to the x would be less than epsilon squared. And I was like, hold on. Epsilon squared is greater than epsilon, right? And so this doesn't seem to be true. Like, we want to show that e to the x is less than epsilon. But we could say that this is less than epsilon for any value of epsilon, for any value of epsilon that's greater than 0 but less than 1, right? Because if I plug in 1/2 squared is 1/4, which is certainly less than 1/2. And so as long as we add this condition on here that epsilon is less than 1, this is still going to be less than epsilon. So it is fair to say that this is true for any value of n greater than or equal to the natural log of 1 over epsilon, so as long as we add the condition that epsilon is sufficiently small, right? We're looking at epsilon values that are close to 0, right? We're not looking at epsilon is equal to 4, because then this would not be true. But I just wanted to add that as a quick side note, because it's a little interesting to be like, hold on, it's not true, but then you think about it a little bit more, and it actually is true. in greater than or equal to the natural log of 1 over epsilon. Yes, just like this definition seems to indicate, that is going to give us y values that are within epsilon of our proposed limit. So that just about sums up our conversation about limits. And the next thing to get into is continuity. And the pretty old school way of defining continuity that you have probably heard of if you took some high school calculus course or an introductory calculus course in college is they say that a function is said to be continuous if you can draw it or trace it on some interval without lifting up your pencil. And so if you think of the function y is equal to x squared, for example, that would look something like this. Here I can come down, and I just drew all of that without having to lift up my pen, right? And so they say that this function is said to be continuous. What functions could you imagine that you wouldn't be able to draw without having to lift up your pencil? One that is pretty immediately obvious to me is the function 1 over x, right? If I had y is equal to 1 over x here, it would look something like this. Here, it would be a very, very small number, and then it would get larger and larger and larger and larger. And what happens here? I have to stop. I would have to go up to an infinite height, and then I would have to come all the way down here and start again. And on this interval from 0 to infinity, hypothetically, if I had infinitely long arms, I could trace this entire function. But there would be no way for me to go from this to this here without lifting up my pencil. Or even the function 1 over x squared, for example. This would be a function that would get infinitely tall from either side as you approach x equals 0. But there would, if you were to get to some arbitrarily high point here on the right side of the origin, there would always be some x value closer to the origin, which would result in a larger y value, and you would have to keep going forever. There would be no way to get from one side of the y-axis to the other without lifting up your pencil. And so for this reason, you'd say that this function is discontinuous at x equals 0, and this is known as an infinite discontinuity. Another function that I could imagine would be impossible to draw without lifting up my pencil would be a function with a hole in it. So let's say we had a function like this, not like that. Something like this. I really wanted to go through that point, but I'm not an artist, as you guys can probably tell. As I get to this point here, I'm going to have a hole. So this is just some linear function, but then at the point x equals 2, there's a hole here. And so if I wanted to trace this, I would go all the way here, and then how would I get from here to here without lifting up my pencil? It would be impossible. And you're like, well, how could you have a function like this? It's such a niche specific function. And yeah, that may be true, but this would just be something like x plus 2 times x minus 2 over x minus 2, right? Because then this would just mimic the behavior of x plus 2 as these factors would cancel, but at the point 2, this function would be undefined. So this is known as a point discontinuity or a hole discontinuity, and this function is said to be discontinuous. For example, here this would be at x equals 2 and a point discontinuity. And another type of discontinuity that we have would be something that looks like this. If I were to draw out my axes here, draw my axes. If we had, let's say y is equal to 1 here, negative 1 here, and we had a function that was just a horizontal line in that direction and a horizontal line in this direction, yes, I could follow this with my pencil forever all the way to negative infinity, and the same is true from 0 to positive infinity. But what happens here? How am I supposed to get from this point to this one without lifting my pencil? And you might think this is a super niche specific function, but this could just be defined as y is equal to x over the absolute value of x. Because for all positive numbers, this would just be x over x, which is just 1. For all negative numbers, this would just be negative 1 over, or negative x over x, right? It wouldn't be negative x, but it would be negative values of x over a positive value of x. And so this would look something like this. This is called a jump discontinuity. A jump discontinuity, and it is discontinuous at x equals 0. I had to make some more space here. There is one more type of discontinuity. It's called a oscillatory discontinuity, but I'm going to talk about that after we talk about the definition of continuity, how we define it, because I think it's a little bit easier to understand once you have that definition in mind. It's not quite as obvious why an oscillatory discontinuity is a discontinuity until you understand the definition. It's not like the picking up your pencil idea doesn't work, and I'll go over that. But first I'm going to talk about continuity at a point, then I'm going to talk about the oscillatory discontinuity, and then I'm going to talk about continuity over an interval. So if we wanted to prove that a function was continuous at some point, how could we go about doing that? Well, let's draw our axes and let's imagine another function. So this is going to be x and y. And we'll have some function here. We'll call this f of x. So this is y is equal to f of x. And then we'll have some point. Let's draw it right here. Point A. And let's say that this routes to a y value of L. How could we express the idea of moving our pencil along the curve without having to pick it up mathematically? Well, you might think to yourself, if the limit as x approaches a of f of x was equal to L from the negative direction, that would be like moving your pencil along from this direction. And the limit as x approaches a from the positive direction of f of x, if that was equal to the same thing, then that would be the same as following your pencil all the way through. Basically, the arrow would just be reversed. You'd be going in that direction to the right instead of going towards it. But if it was true that as you got closer and closer and closer from the positive direction as we're moving towards that point, if y values got closer and closer to L, then it would be true that as you moved away from it, you would be able to do that in one fell swoop. So if you might think to yourself that saying that both of these two things is true, which is the same thing as saying that the limit as x approaches a of f of x was equal to L. If you might think to yourself that if this was true, then that would be sufficient to prove that the function was continuous at that point. And that's almost correct. It's almost correct. But we do need to add one more condition on here, because we could imagine a function like this. We could imagine some function that exhibits some behavior, and then there's a hole, and then it keeps going. And let's say that this hole has the height L, and the limit as you approach a of this function equals L, but the function is defined somewhere else above that. This right here is actually f of a. And you would not be able to draw this function without picking up your pencil. You just would not be able to do it. You would have to come to this hole, lift your pencil up, draw this dot, and then go back to it. So if the limit as x approaches a of f of x is equal to L, and f of x is equal, I should say f of a, because that's where we're approaching from. If the limit as x approaches a of f of x is equal to L, and f of a is equal to L, then the function is continuous at that point. All right, now that we understand the definition of continuity, that both of these conditions must be true, we could talk about this oscillatory discontinuity. So I'm not even going to begin to try to draw this function, because it gets a little tough near x equals 0. But this is going to be the function y is equal to sine of 1 over x. And I just plug this into Wolfram alpha to get the picture. So the behavior of this function, sine is going to be a function that oscillates, right? It goes back and forth between two different values, right? And as you get closer and closer and closer to 0, this function is going to oscillate more and more rapidly. The reason being that 1 over these smaller and smaller and smaller numbers that you get as you approach 0 is going to yield bigger and bigger numbers that are going to change faster and faster and faster as you get closer to the point x equals 0. And at the point x equals 0, this function is going to be undefined because you can't divide by 0. So if this is f of x, if f of x was equal to sine of 1 over x, then at the point x equals 0, first of all, f of 0 does not exist, undefined, right? So we already know that this function cannot be continuous at the point. But more so, the limit as x approaches 0 of f of x here, you might at first think like, okay, well, yeah, this is changing more and more rapidly, but it looks like you can follow your pencil, like you would just be changing more and more rapidly. As you get closer and closer to 0 from the negative direction, this function is going to produce values that are opposite of the functions that you're going to get, of the values that you're going to get on the right side of the origin. The reason being that basically on the left side here, you're dealing with negative x values. So essentially, you're dealing with sine of negative 1 over, or I should say 1 over negative x. And sine of negative x is equal to sine of 0 minus x. We could agree that that's true. And you can use the difference, sum and difference formulas or identities of trigonometric functions to show that this is equal to sine of 0 cosine of negative x minus cosine of 0 times sine of negative x. Right? This is just the difference formula for sine. Sine of 0 is just 0, so this term is going to go away. And cosine of 0 is equal to 1. And so this is just equal to negative sine of x. This negative shouldn't be here. Right? And so for this reason that we just showed right here, sine of 1 over negative x is going to equal negative sine of 1 over x. So the values on the left side of this are always going to be opposite the values on the right side. So this limit does not exist for two reasons, right? If one wasn't enough. This isn't a very pure mathematical analysis, because really this is a function that's just going to oscillate between two values faster and faster and faster, regardless of what happens. So the limit clearly can't exist. It's going between two different things. It's not going to settle down on one value. But also, as you approach, even if there was some hypothetical closest value that you could get to the origin, to the point x equals 0, the value of that function on the right side, as you approach from the right side, would equal the opposite of as what you would get as you approach from the left side. So there's just so many different things going on here. This limit does not exist at x equals 0, and the function is not defined at that point. So for this reason, it is not continuous at x equals 0, and this is an example of an oscillatory discontinuity. I hope that makes a little bit of sense. I know that that's not 100% mathematical. It's a little bit abstract, but I hope that makes sense. I should point out here before I move on, there's another little mistake here. This also should not be negative x. This should also be positive x. This is the sum and difference formula for sine. It's just a little bit of a brain fart on my part, but it states that sine of alpha minus beta is equal to sine of alpha times cosine beta minus cosine alpha sine beta. And you could see here that this shouldn't be negative x, it should be x according to this formula. So I just want to point that out. There's just a little bit of a mistake on my part. All right, so moving on here, let's do an example of continuity at a point. Proving continuity at a point. Let's just do one little example before we move on. So let's switch it up a little bit and let's talk about the function y is equal to x cubed. Y is equal to x cubed, and let's talk about it at the point 2. X cubed is going to look something like this, of course, and at 2 it would route to 8, right? So this is y is equal to x cubed. And so we need to show two things. If we want to prove that x cubed is continuous at the point 2, x equals 2, then we need to prove that 2 cubed is equal to the limit as x approaches 2 of x cubed. This is what we want to show, right? And 2 cubed is going to equal 8. So really what we're trying to show here is that the limit as x approaches 2 of x cubed is equal to 8. If we could show this, then we've proven that this function is continuous at that point, because we've shown that f of 2 is equal to 8, and the limit as x approaches 2 is equal to 8 as well. And if we want to show that this is true, that the limit as x approaches 2 of x cubed is equal to 8, then we have to show that for any epsilon greater than 0, there exists some delta greater than 0 such that the absolute value of x cubed minus 8 is going to be less than epsilon, and the absolute value of x minus 2 will be less than delta. We have to show that this is true if we're going to prove that the limit here is equal to 8. And so how could we go about dealing with this? Just like with the other Epsilon-Delta proofs, we want to try to get an x minus 2 here so that we can find some relationship between delta and epsilon. And so one way you might think to do that is to just factor that out of this expression. If we were to divide x cubed minus 8 by x minus 2, what would we get? Well, x minus 2 can go into x cubed x squared amount of times, right? And then you would be left with x cubed minus 2x squared, and when you subtract that, you get 2x squared positive, because you're subtracting a negative minus 8. And then how many times can x minus 2 go into that? Well, if you multiplied by 2x, then you would get 2x squared minus 4x. Subtracting this, you would get 4x minus 8. And then here, that's just 4 times x minus 2. And we actually get a remainder of 0. So this is to say that this would be equal to absolute value of x minus 2 times the absolute value of x squared plus 2x plus 4. And one thing we might think to do is to use the triangle inequality here and then say that this is just equal to the absolute value of x minus 2 times the absolute value of x squared is always going to be positive, so that's the same as x squared, plus 2 times the absolute value of x plus 4, right? The absolute value of positive 4 is always just positive 4. And we want this to be less than epsilon. And we're kind of stuck here. We can't just, this isn't like x squared where you take a square root and call it a day. We can't just divide both sides by x squared plus 2 times the absolute value of x plus 4, because our proposed value for delta can't depend on x. X is introduced in this definition after delta, so it wouldn't make any sense if delta were to depend on x. So what are we supposed to do here? How are we supposed to get rid of this factor here and just be left with the x minus 2 so that we can derive some relationship between epsilon and delta? And I encourage you to pause the video here and try to figure this out on your own. I'll give you a hint. You're gonna have to do something new that we haven't done at least in my videos. And the trick here is that you want, I'll just give another hint, you want to restrict the x values to where they are close around the point of interest. All right, so if you paused it and gave it a try on your own, that's great, but let's see how I would deal with this. So coming back to our graph here, if we want to, let's say that we restricted delta to be less than 1. If that were true, then the absolute value of x minus 2 must be less than 1. So we would be looking at x values that are within this interval here from 3 to 1. X would have to be less than 3 and greater than 1. And so if that was true, then it would be safe to say that the x squared plus 2 times the absolute value of x plus 4, this would have to be less than 3 squared plus 2 times the absolute value of 3 plus 4, right? Because it can't be 3. X has to be less than 3 and greater than 1. And so if we take delta being less than 1, then this must be less than 3 squared plus 2 times the absolute value of 3 plus 4. 3 squared is 9, 2 times 3 is 6, 9 plus 6 is going to be 15 plus 4 is 19. So this must be less than 19, right? So if we take delta as less than 1, then this becomes the absolute value of x minus 2 times 19. And this must be, we want this to be less than epsilon. And this is the same as the absolute value of x minus 2 being less than epsilon over 19. And now we have found the delta that we're looking for, right? We want delta to be less than epsilon over 19, right? But also we want to assume that delta is less than 1 as well. So in conclusion, if we say that delta is less than the minimum of 1 and epsilon over 19, then we know that the absolute value of x minus 2 will be less than epsilon over 19, right? And this is to say that it's the same as the absolute value of x minus 2 times 19 being less than epsilon. And we know from our previous reasoning that if delta is the minimum of these two, then the absolute value of x minus 2 times the absolute value of x squared plus 2x plus 4 will be less, it must be less than the absolute value of x minus 2 times 19, which is less than epsilon. And we know that this, from the beginning, we know that this is the absolute value of x cubed minus 8. And if it's less than this, which is less than epsilon, then this must be less than epsilon. And we have shown that the Epsilon-Delta definition holds up at this point, and the limit as x approaches 2 of x cubed is equal to 8, right? And if we know that the limit as x approaches 2 of x cubed is equal to 8, and 2 cubed is also equal to 8, then for these two reasons, f of x must be continuous, or I'll put is continuous at x equals 2. So we got a little bit of practice here with the epsilon-delta definition. We introduced this technique of limiting our delta value a little bit just to make it a little bit easier. And I do want to show real quick before we move on that there's nothing special about this delta being less than 1 that we decided to go with. Let's try to do the same thing with delta being less than 1/2, for example. Then the smallest it could be would be 2.5 cubed plus 2 times 2.5 plus 4, and you would have to evaluate whatever this is. 2.5 cubed is nasty, but 2 times 2.5 is 5 plus 4, which is just 9, and so this would be 2.5 cubed plus 9, and so you would just have to restrict delta to be the minimum of 1/2 and epsilon over 2.5 cubed plus 9, right? You could do it in the same way, and then if you work that out, it would show the exact same thing. The reason I went with 1 is just because it makes the math easier than you're dealing with just smaller numbers, whole numbers, things like that. But there's nothing special about this 1 here. You can use anything. All right, so let's press forward and talk about continuity over an interval. Continuity over an interval is a little bit more fun here. So continuity over an interval. If we want to show that a function is continuous over some interval, then the way we can do that is by showing that the function satisfies the definition for continuity for every x value over that interval. Right, so how could we show that? Well, first of all, it's important to note that we can sum up the definition for continuity in one simple statement, which is to say that the limit as x approaches c of f of x is equal to f of c. If this is true, then f of x is continuous at x equals c. Right, and this should make sense. We're saying that f of c exists, and if the limit as x approaches c of f of x is equal to f of c, then f of c exists, the limit exists at that point, and the limit is equal to the function evaluated at our point. Those are our 3 conditions for continuity. So if this is true, then this function is continuous at that point. And so it's safe to say that if the limit as x approaches c of f of x is equal to f of c for all x values over some interval from a to b, then f of x is continuous on the interval from a to b. Right? This should make sense. And so let's get into actually demonstrating that. And I should fix this up really quick. This is an element. X is on this interval, basically. And so in order to do this, let's try to prove that x squared is continuous for all real numbers. Okay, so how would we go about showing this? Well, we want to show that the limit as x approaches c of f of x is equal to f of c for all real numbers. And if we want to show that, then we have to look at our epsilon-delta definition. This means that for any epsilon greater than 0, there exists some delta greater than 0, such that the absolute value of f of x minus f of c will be less than epsilon, and the absolute value of x minus c will be less than delta. Okay, so how can we go about showing this? Well, f of x is going to be x squared, and f of c is going to be c squared, right? That should be pretty intuitive. And this right here is just the difference of 2 squares. This is x plus c times x minus c. And so we can break this up. This is equal to the absolute value of x minus c times the absolute value of x plus c, and it is less than epsilon. Now, at first you might be tempted here to just say, well, oh, look, we have absolute value of x minus c right here. That's very similar to our delta definition here. Can't we just divide both sides by x plus c and call it a day? And while that might seem to intuitively make sense, we have to understand that with this definition, we are dealing with x values on the interval from c minus delta to c plus delta, right? These are the x values that we're dealing with. And so our x values are really it's an entire interval of x values, and they are going to depend on the delta that we're given. If we're given delta is equal to 0.1 and c is equal to 3, then we're dealing with x values that consist of the entire interval from 2.99, did I say 0.1? So from 2.9 to 3.1, right? If our delta was to depend on x, then the delta would have to change as we moved along that interval. The delta value would have to alter as we move from 3 to 3.01 on the way to 3.1, and that can't happen. Delta has to stay the same. X depends on delta, right? And so our definition for delta cannot depend on X. And so we have to think of some way to get rid of this X plus C term here. All right, and so in order to do that, let's defer to the triangle inequality here. So we have the absolute value of X minus C times the absolute value of X plus C. This is going to be less than or equal to the absolute value of X minus C times the absolute value of X plus the absolute value of C, right? And let's think about the absolute value of X here. I could rewrite this as equal to the absolute value of X minus C plus C. That's the same as the absolute value of X. And it would be safe to say that this is less than or equal to the absolute value of X minus C plus the absolute value of C. This is just a triangle inequality again. And so if we take our trick that we learned earlier and we say that, okay, well, we want to deal with delta values that are sufficiently small, right? Because we're trying to prove that the limit exists. Let's deal with delta values that are less than or equal, or let's deal with delta values that are less than 1, right? And if delta was less than 1 and absolute value of X minus C is less than delta, then that means that this must be less than 1. And so we could say that this is less than 1 plus the absolute value of C. And that should make sense. And so if we add this little condition here, if we say if delta is less than 1, then what happens? Well, right here, this absolute value of X is going to be less than, let's say, the absolute value of X minus C, and then this is going to be less than the 1 plus the absolute value of C, and then you have the absolute value of C again. And so this would be less than 1 plus 2 times the absolute value of C, right? We know that the absolute value of X is less than 1 plus the absolute value of C, and so this would be less than 1 plus the absolute value of C plus the absolute value of C, which is equal to 1 plus 2 times the absolute value of C, right? And so now we can reimagine our epsilon here, and we can divide both sides by the absolute value of 1 plus 2 times the absolute value of C. Absolute value of 1 plus 2 times the absolute value of C, and we can do that here. And the absolute value of 1 plus 2 times the absolute value of C is really just the same as 1 plus 2 times the absolute value of C, right? And so we could say that if delta is less than the minimum of 1, or epsilon over 1 plus 2 times the absolute value of C, then the absolute value of X squared minus C squared is going to be less than epsilon, and the absolute value of X minus C is going to be less than delta. Therefore, X squared is continuous. Well, actually, let's not skip steps in our reasoning. So because of this, therefore, the limit as x approaches c of f of x is equal to f of c for all real numbers. Therefore, f of x, which in this case is going to be x squared, is continuous for all real numbers. And I should change this. I'll rewrite this as x squared. The limit as x approaches c of x squared is going to equal c squared, just to be more specific. So I'll rewrite that now. All right, and this is how we show that this function is continuous for all real numbers. All right, let's look at one more example, but let's try to challenge ourselves a little bit. So I'm going to make some space here. And let's try to prove that sine of x is continuous for all real numbers. This one's going to be a little bit of a challenge. I encourage you to pause and try that on your own. Okay, but moving forward. So if we want to prove this, we want to prove that the limit as x approaches c of sine of x is equal to sine of c for all real numbers. Okay? And if we want to show this, then we have to show that the absolute, or the epsilon-delta definition, absolute value of sine of x minus sine of c, this is f of x, f of c, is going to be less than epsilon, and the absolute value of x minus c is going to be less than delta. And before we press on here, let's remind ourselves of these trigonometric definitions. If we have sine of a plus b, we know that that's equal to sine of a cosine b plus cosine a sine of b. And if we have sine of a minus b, we know that this is equal to sine of a cosine b minus cosine a sine of b. And coming from this is going to be a pretty important one for dealing with this right here. If we can subtract these two, then we get that sine of a plus b minus sine of a minus b. What is this going to equal? Well, these are going to cancel, and we're going to get 2 cosine a sine b. Right? We'll just add these two together because we're subtracting a negative that's adding. And I'm going to let x equal a plus b. And I'm going to let a minus b, or y, equal a minus b. I'm going to let these variables equal that. Well, then what do we get? We get that sine of x minus sine of y is equal to 2 times the cosine. Well, what do we get for a here? If we take these two equations and we add them together, these b's are going to cancel and we'll be left with 2a. And what we get is that x plus y is equal to 2a. And so a is going to equal x plus y over 2. So we have 2 times the cosine of x plus y over 2. And we're going to be multiplying by sine of b. What's b in this case? Well, we could do the same thing. We could subtract these two equations. We get x minus y is equal to 2b. Once again, we're subtracting a negative. That would add it. Well, then b just becomes x minus y over 2. Right? Sine of x minus y over 2. And so that's where this little definition comes from. Sine of x minus sine of y is equal to 2 cosine of x plus y over 2 times sine of x minus y over 2. And we're going to use that over here. So we want to say that this is equal to the absolute value of 2 times the cosine of, in this case, we were dealing with x and c. This would be x plus c over 2 times the sine of x minus y over 2. And this shouldn't be a y, this should be a c. Sorry about that. Change that. Oh, goodness. What a mess. I'm just going to do it like this. X minus c over 2. Okay, and why is this useful? Well, cosine and sine fall on the domain from -1 to 1. So the value is always going to be between -1 and 1. And if we're dealing with the absolute value here, that means that really the value is going to always be between 0 and 1. Because we can't have a negative number. This is inside of absolute value signs. Right? And so it's safe to say that the absolute value of 2 times cosine of x plus c over 2 sine of x minus c over 2, it's safe to say that this is less than or equal to the absolute value of 2 times sine of x minus c over 2. Because the biggest number that this cosine of x plus c over 2 could be is positive 1. And that would make it equal to. Every other number that this could be would make this less than that. So this is less than or equal to this. And this is less than epsilon, which means that the absolute value of 2 times sine of x minus c over 2 is going to be less than epsilon. Right? And I actually think we're ready to prove this here, because if we know that the absolute value of x minus c is less than delta, then surely the absolute value of x minus c over 2 must be less than delta. And there should be no confusion there. The absolute value of 2, I'm going to write this here. 2 times the absolute value of sine of x minus c over 2, which is this right here, that's going to be less than 2 times the absolute value of x minus c over 2, because sine of x is always going to be less than x, right? And this is less than, well, let's see, if this is less than delta, then we can say that that's less than 2 delta, right? And if delta is less than or equal to epsilon over 2, or if we say that delta is less than, I should say, if delta is less than epsilon over 2, no, it could be equal, right? Yeah, it could be equal. If delta is less than or equal to epsilon over 2, then what happens? Well, this just becomes epsilon, because epsilon over 2 times 2 is epsilon. We can ignore this middle term, and we get 2 times the absolute value of sine x minus c over 2 will become less than epsilon. And if this is true, then the absolute value of 2 sine x minus c over 2 must be less than epsilon. And it also must be true that the absolute value of 2 times cosine of x plus c over 2 times sine of x minus c over 2 will be less than epsilon. Of course, because this factor must be between 0 and 1, this is going to be less than that. Or it'll be less than or equal to this, which is less than this. So therefore, this is going to be less than epsilon. And we know that this is equal to sine of x minus cosine, or sine of x minus sine of c. And so we've shown that if delta is less than epsilon over 2, delta is less than or equal to epsilon over 2, then the absolute value of sine of x minus sine of c is less than epsilon. Therefore, the limit as x approaches c of sine of x is equal to sine of c for all real numbers, and sine of x is continuous for all real numbers. Whew, that was a challenging little example there. Hope y'all enjoyed that, and we're ready to move forward. And we're going to move forward with intermediate value theorem. Intermediate value theorem, also known as IVT, tells us, and I'm just going to write the theorem first, then we're going to talk about what it means. Wow, my handwriting is bad. So intermediate value theorem tells us that if f of x is continuous on the interval from a to b, then and there exists some k such that it is on the interval between the minimum of f of a and f of b and the maximum of f of a and f of b. if f of x is continuous on the interval from a to b, and there exists a k that is between f of a and f of b, then there exists some c on the interval between a to b such that f of c is equal to k. Wow, that's confusing. I bet that's mostly confusing because of this part right here, but we're going to talk about what that means. So let's do this with some graphs. Okay, I'm going to draw two just so we can clear up any confusion about this if there exists any at all. I do encourage you to pause and think about this if you are a little bit confused. So I'm going to draw two graphs here. I'm going to draw one that looks like this and one that looks like this. And I'm going to draw an A here and a B here. And I'm going to have an A here and a B here. Okay, so what this theorem is telling us is that we are talking about a K that is between f of A and f of B. So in this case, right here, this is like, I guess, the ordinary case. You would have K is greater than f of A, but less than f of B. And the reason for that is because f of B is greater than f of A. And because f of B is greater than f of A, then the minimum of f of A and f of B would be f of A. And so this would be on the interval, and the maximum would be f of B. And so this would be on the interval from f of A to f of B. But here, if you're wanting to talk about a k that is between these two values, so let's say that our k in this case would be here, for example, and let's say that our k in this case would be here. If you wanted to talk about a k that is between f of A and f of B, here you would have to say that it is greater than f of B. That k would be greater than f of B, but less than f of A. And the reason is because this function is decreasing. And if that were the case, because it's decreasing on the interval, then in this case we would have to select, because f of A is greater than f of B, we need this inequality to be satisfied. And here, the minimum of f of A and f of B would be f of B. And so the reason we have this minimum maximum thing is to make this true, whether it's a function that's increasing or decreasing. We're simply talking about a value of k that is between f of A and f of B. That's what this function is dealing with. Whoa, that's terrible. Right here. And so now we can get rid of one of these graphs now that we understand that min-max idea and why that has to be in the theorem, because some functions can be increasing and some functions can be decreasing. And now we can move forward with what this is actually telling us. So I'm just going to move this here, make it a little bit more centralized, and we can move forward. So this tells us that if f of x is continuous on the interval from a to b, and there exists some k that is in between f of a and f of b, then there must also exist some c on that interval from a to b. It must be on the interval from a to b such that f of c is equal to k. And so what does that tell us? Well, that tells us that if f of x is continuous on some interval, and I give you a value k that is in between f of a and f of b, then there must always exist some x value that is in between a and b that will yield k as a result if I plug in f of c. That's what intermediate value theorem tells us. And so how can we go about proving that? Well, the way that this proof is generally done is that we consider a set first. We consider a set S, and this is going to consist of all the x values on the interval from a to b, and actually we'll include a and b in this interval. This is going to consist of all the x values on the interval from a to b such that f of x is less than k. Right? And so this is going to talk about all the x values where when you plug in x onto this interval, then the value of f of x will be less than k. So here you see that the value of f of x is less than k, less than k, less than k, less than k, and then boom, here it stops. And so it's going to consist of all of the x values on this interval here. This is our set right here. It's this little range of x values. And we're going to let C be the supremum of S. And a supremum is just a fancy word that says the smallest possible value which is greater than or equal to every value in this set. So it's the smallest number I can give you that is greater than or equal to every single value in this set. Okay? And because f of x is continuous, on the interval, we know that the limit of, as x approaches any value on that interval, we'll just say c, of f of x must equal f of c. And that means that we also know that the limit as x approaches a here is going to equal f of a, right? And so values that are sufficiently close to a, even on the positive end or the negative end, but we're talking about the positive end here because we're considering this interval. Values that are sufficiently close to a are going to produce values that are sufficiently close to f of a. That's what the definition of a limit tells us. And so a cannot be the supremum of this set. A cannot be c. And the same thing goes for b. Values that are sufficiently close to b must produce values that are sufficiently close to f of b. Right? They can't produce values that are anywhere near, like it cannot be c. It can't produce values that are anywhere close to k. Right? And so both of those values are out. And I want to be clear here, what I mean when I say those values are out is that those values cannot be the supremum of this set. B cannot be the supremum because values that are sufficiently close to it must produce values that are sufficiently close to f of b, which clearly is not the smallest number that is greater than or equal to every value in S. It's significantly greater. Values that are sufficiently close to A are going to produce values that are sufficiently close to f of A. And so that's going to be less than k. That will be included in the set. It clearly is not going to be the supremum because it's not the smallest number that it's greater than or equal to everything in the set. It's going to be somewhere in the lower end of the set. Right? And so neither A nor B can be the supremum of the set C. And we're trying to figure out what C is. One thing that we do know about C is, again, because f of x is continuous on this interval, we know that the limit as x approaches c of f of x is going to equal f of c. Or in other words, for any epsilon greater than 0, there exists some delta. We should be very well versed in this by now. There exists some delta greater than 0, such that the absolute value of f of x minus f of c is less than epsilon, and the absolute value of x minus c is less than delta. Should be very familiar with this by now. And if this is true, it stands to reason that if c is the supremum of S, then there must exist some x naught, we'll just call it x naught, on the interval from c minus delta to c inclusive, such that f of x naught is going to be less than k. This must be true, otherwise c would not be the supremum of the set. Some value to the left of c would be the supremum. If there was no value to the left of c such that f of that value was less than k, then c would not be the supremum of that set, because if there must be, if C is the supremum of that set, then there must be some value to its left that satisfies the conditions of the set, namely that f of that value is less than k. So this must be true. And we also know that if f of x naught is, if x naught is on the interval from c minus delta to c, then f of x naught must be on the interval between f of c plus epsilon and f of c minus epsilon. The reason being is because x naught is going to be on this interval between c minus delta and c plus delta. It must be on that interval, and all of the x values within that interval are going to route to y values that are within epsilon of f of c, right? So we know that f of x naught must be on this interval between f of c minus epsilon and f of c plus epsilon. And if we know that this is true, then we can just add epsilon to all sides here. We could say that f of c is going to be less than f of x naught plus epsilon. And f of x naught is less than k, and so we know that this is going to be less than k plus epsilon. Therefore, f of c is going to be less than k plus epsilon. I hope that's in the frame. And similarly, we also know that there must exist some x, and we'll call this one x1, and you probably see where I'm going with this. This is going to be on the interval from c to c plus delta. There must exist some x on that interval such that f of x naught was, or f of x1, we're talking about x1 here, was greater than k. This must be true, otherwise c would not be the smallest value that is greater than or equal to every value in the set. It would not be the supremum of the set. Some value to its right would be, right? And once again, we know that if x1 is on this interval between c minus delta and c plus delta, which it is, then f of x1 must be on the interval between f of c minus epsilon and f of c plus epsilon. Right? And if we subtract epsilon from all sides here, then what we get is that f of x1 minus epsilon is going to be less than f of c. And this is going to be, if f of x1 is greater than k, then this is going to be greater than k minus epsilon. And if that is true, then we know that f of c must be greater than k minus epsilon. F of c must be greater than k minus epsilon. Right? And if we know that f of c is greater than k minus epsilon, and we know that it is less than k plus epsilon, the only way that this could be true for any value of epsilon is if f of c was equal to k. That would be the only way that that would be possible. And therefore we have proven that there must be some c in between a and b such that f of c is equal to k. And that's intermediate value theorem proven.